Welcome students. Today we have discussed a most valuable and important lemma in the probability theory that is included in the syllabus of B.SC Mathematics Honours and B.STAT and B.TECH. We have to study about TCHEBYCHEFF'S lemma. So, we want to discuss here TCHEBYCHEFF'S lemma. This lemma a important role in the probability theory and it have many used in the probability. So first we state the lemma. If X is a positive random variable with finite mathematical expectations, then for any real parameter t, probability of x less or equal to mu t square greater than equal to 1 minus 1 by t square, or probability of x greater than mu t square less or equal to 1 by t square. Now we want to prove this lemma. Case 1. First we have to consider the discrete case. Discrete case. Let x is a random variable which x is a discrete random variable, obviously x is a discrete random variable which can take the values x1, x2, x alpha plus 1 and so on. Then we have mu equal to expectation of x, that is equal to summation over x alpha probability of x equal to x alpha. That is the definition of expectation. So expectation of x equal to some x alpha probability of x alpha, the product, and summation over x alpha. Here probability of x equal to x alpha equal to p alpha. Now for any t, let x alpha equal to mu t square. So we divided this sum into two parts. First one is x alpha less or equal to mu t square, x alpha into probability of x equal to alpha, that is p alpha, plus summation of x alpha greater than mu t square x alpha p alpha. We divided this sum into parts. First one is x alpha less or equal to mu t square and second one is x alpha greater than mu t square. As p alpha greater than 0 and x alpha equal to mu t square, that is also greater than 0, and so we have mu greater than equal to summation of x alpha, summation over x alpha greater than mu t square x alpha p alpha, that is equal to mu t square summation of p alpha, summation will be taken over x alpha greater than mu t square. Therefore, mu greater than equal to mu t square probability of x greater than mu t square. From this, x greater than mu t square. If we cancel from the both side the term mu, we have 1 by t square greater than equal to probability of x greater than mu t square, that is probability of x greater than mu t square less or equal to 1 by t square. As a consequence, we find probability of x greater than equal to mu t square x less or equal to mu t square greater than equal to 1 minus 1 by t square. So for discrete case, we already proved the two parts. First one is probability of x greater than mu t square less or equal to 1 by t square, and as a consequence probability of x less than equal to mu t square greater than equal to 1 minus 1 by t square. Now we consider the continuous case. Case 2, if x is a random variable which has the continuous probability distribution with probability density function fx, with probability density function fx, we have mu equal to expectation of x, that is equal to 0 to infinity x fx dx. We divide this integration from 0 to mu t square x fx dx and integration mu t square to infinity x fx dx. As this part is greater than 0, so we write mu greater than equal to integration mu t square to infinity x fx dx, that is greater than equal to mu t square into probability of x greater than mu t square. If we cancel the term mu from the both sides, we write 1 by t square greater than equal to probability of x greater than mu t square, that is probability of x greater than mu t square less or equal to 1 by t square. So we have proved this. Now from this we write 1 minus probability of x less or equal to mu t square less or equal to 1 by t square, that is probability of x less or equal to mu t square greater than equal to 1 minus 1 by t square. So we have proved this part. So here the lemma we have already proved, and it's a very important lemma, and using this lemma we prove the TCHEBYCHEFF'S inequality. TCHEBYCHEFF'S inequality. Using this lemma we prove TCHEBYCHEFF'S inequality. First we state the inequality. If x is a random variable, if x is a random variable having finite variance, sigma square and mu equal to expectation of x, then for any real parameter t, probability of mod of x minus mu less or equal to sigma t greater than equal to 1 minus 1 by t square. So first we look what is the difference between TCHEBYCHEFF'S lemma and TCHEBYCHEFF'S inequality. The lemma said that x is a positive random variable, but here the term positive is omitted from this. Only x is a random variable having finite variance sigma square and expectation x. Then for any real parameter t, probability of mod of x minus mu less than equal to sigma t greater than equal to 1 minus 1 by t square. Now we want to prove this lemma, this inequality. Consider y equal to x minus mu whole square, x minus mu whole square. So here y greater than 0, y is a random variable that is greater than 0. So we use TCHEBYCHEFF'S lemma because TCHEBYCHEFF'S lemma says that x is a positive random variable with finite mathematical expectation. Then for any real parameter t, probability of x less or equal to mu t square greater than equal to 1 minus 1 by t square. So using TCHEBYCHEFF'S lemma, TCHEBYCHEFF'S lemma on y we have probability of y less or equal to sigma square t square greater than equal to 1 minus 1 by t square. You have asked a question, in TCHEBYCHEFF'S lemma says probability of x less or equal to mu t square greater than equal to 1 minus 1 by t square. In place of mu, we write here sigma square. So what is sigma square? Sigma square is nothing but the expectation of y. What is y? Now y is x minus mu, expectation of x minus mu is whole square, and that is the variance. So in place of mu, that is the expectation of x, we write, as we have used TCHEBYCHEFF'S lemma on y, so here the term sigma square represents expectation of y, and therefore probability of y less or equal to expectation of y t square, that is sigma square t square, greater than equal to 1 minus 1 by t square. That is probability of, right, y is x minus mu whole square less or equal to sigma square t square greater than equal to 1 minus 1 by t square. That is probability of modulus of x minus mu less than equal to sigma t, less than equal to sigma t greater than equal to 1 minus 1 by t square. So we have reached the target, that is probability of